So in this module, we're going to cover, well, a lot. We're going to cover electrolytes, but within electrolytes, we've got strong bases, strong acids, solubility rules, and just electrolytes in general. What is an electrolyte? So as you start this section, I want you to make sure to review naming, formulas, and charges of all of your ions. So that's back to your Chapter 3 material. You should understand the terms for solution, solvent, solute, and aqueous solutions. So, naming and formula, can you convert back and forth between them? Charges on ions, that is important as well. That also factors into those naming and formulas. Solution, a homogeneous mixture. Solvent is usually present in a greater amount, and it's whatever does not change phase. You dissolve something into the solvent. Your solute is what you've dissolved. You dissolve your solute into your solvent. It's usually present in a smaller amount, and if one thing changes phase, it's your solvent that's going to change phase. Aqueous solutions mean dissolved in water. So make sure to review that if you're not comfortable. First thing I want to talk about is the light bulb demonstration and electrolytes. So I'm going to flip over. We're going to watch YouTube video really quick with this actual video because I can't seem to get it to play straight out of here. I'll be able to play it in class, but in the video itself, I'm not tech savvy enough to figure out how to show you guys that without flipping over to a different app. But in the light bulb demonstration, I want you to watch what happens in solution to cause some of the solutions to conduct electricity. And I want you to think about what is electric current. Based on that definition, I want you to think about what substances are forming in solution and how this conducts electricity. So let's go ahead and watch this video.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve a material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water. As the sugar dissolves, the light does not light up, so sugar is a non-electrolyte. Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water, and about 10 drops will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
Stressing over back to school shop.
So I love that video. I've used that video for teaching for years now because it's just simple, short, and shows you what we see with no electrolyte, weak electrolyte, or strong electrolyte. So going back to this question, what is electric current? When you think about electrical current, what should you see? What you need to see here is there's a flow of charge. We've got electrons that are going to flow. That's what's going to light up the light bulb. We've got cations, your positively charged ions, and we've got anions, which are your negatively charged ions, all floating around in solution, allowing those electrons to transfer. So, based on that definition of electrical current, substances that form ions in aqueous solution will be able to conduct electricity. And that's what we saw in the video. We saw that when he had just pure water, deionized water, no electrical current, nothing happened. The light bulb did not light up. When he put sodium chloride inside, we saw that the light bulb lit up very brightly. When he used sugar, nothing happened. And when he used a weak acid, acetic acid, which is vinegar, we saw the light bulb light up, but it was very weak. The only thing that he did in the video that we don't have listed in our little diagram down here is if we have a strong acid, he used HCl, and strong acids behave like sodium chloride did because strong acids are strong electrolytes. Strong acids, strong bases, and soluble salts. See if I can fit this in here. For weak electrolytes, we have weak acids and weak bases. And compounds that are not soluble or molecular compounds will be non-electrolytes. I'm going to write all of that down on another slide so you don't have to try to copy it down and scrape it down from here. But I want you to think about that when we go through this section. It's a strong electrolyte for, say, sodium chloride or your strong acid, strong bases because they completely ionize in solution. We talked about that solution formation of that sodium chloride and how it breaks up into the individual ions that are then surrounded by water molecules and float around in solution. When that happens, those ions floating around is what lets our charge transfer. Hence, the light bulb lights up. So, electrolyte or non-electrolyte, how do we decide? Well, your electrolyte will have ions that are freely moving in solution. Electrolytes as a whole have ions freely moving around. They can fall under strong or weak, but strong electrolytes have a lot of ions floating around. So the way we actually do it, we will write strong electrolytes when we're writing a balanced chemical equation, we write a one-headed arrow. Strong electrolytes are defined as a substance that completely 100% dissociates in aqueous solution. Weak electrolytes still have those ions present, we just have fewer of them. So let's go ahead and write down these definitions. For strong electrolytes, we're going to define a strong electrolyte as a substance that completely, meaning 100%, dissociates into ions in aqueous solution. Weak electrolytes have few ions. So, well, let me back up one thing really quick. Strong electrolytes, when we say that it completely dissociates into solution, what does that really mean? It means it conducts a lot of electricity. We see the light bulb light up really bright. Weak electrolytes only, they have few ions in solution. So let me write weak electrolyte over here. A weak electrolyte, first of all, we don't write a one-headed arrow, the arrow like normal. We write what we call an equilibrium arrow. We see here that this is not the same thing. Do not write these arrows with a double head. This is a resonance arrow. We write arrows like this. They're called equilibrium arrows. And we use these arrows because on a weak electrolyte is a substance that only partially ionizes in aqueous solution. In practice, that means it only conducts a little electricity. Hence, the light bulb doesn't light up very big or very bright. And then, of course, we have non-electrolytes, which are those uncharged particles like we saw with sugar. Let me go ahead and erase them so we have some space I can write that definition down. I do apologize. Normally I write this stuff on a whiteboard. Okay, so non-electrolyte, substance that is soluble in water. So like we saw sugar. Sugar will dissolve in water, but does not conduct an electric current when dissolved in water because they're non-charged particles. The molecules do not break apart. So things like non-electrolytes will be like sugars and alcohols. Your electrolytes will be your soluble salts, strong acids, and strong bases. Weak electrolytes are weak acids, weak bases. So how do I know if a salt is soluble? Well, that's where our solubility rules come into play. We do have to memorize these. You can't get around that. It is one of the things you're going to have to memorize. And this is actually determined by experimentation. So for ionic salts, when we say soluble salt, it will be an ionic salt, and we want to ask ourselves, is it soluble or insoluble? This, again, is determined by experimentation. We will go through the solubility rules, but you are responsible for memorizing them. For acids and bases, how do we determine if they're strong or weak? This also actually comes down to experimentation. This was all determined by experimentation, but you will have to memorize there are 7 strong acids and 8 strong bases. The 7 strong acids I just have memorized. The 7 strong bases, there is a method to follow on the periodic table to help you memorize them, and I'll cover that. But if it doesn't fall under the grouping of strong, then it's by definition weak. We're going to talk a lot more in second semester about what actually makes these strong and weak, but it does come down to if I put a strong acid in water, it completely breaks apart like sodium chloride. So we talked about how sodium chloride goes into water and forms sodium ions and chloride ions. Well, HCl is a strong acid. HCl in water, I have protons and chloride ions floating around. I don't have HCl molecules floating around in solution anymore. They break apart 100%. In weak acids and bases, so strong acids, strong bases is the same thing. They break up virtually. We say ionized virtually because, I mean, there is limits to everything, yes. But you can assume for all intensive purposes they're going to completely ionize or dissociate 100%. Weak acids and bases ionize or dissociate only a small percentage. And it's based on temperature, it's based on concentration. But what we see is hydrofluoric acid is a weak acid. We do use our equilibrium arrows because it is an equilibrium, and some of it will dissociate, forming protons and fluoride ions. So the reason we use these equilibrium arrows is because some of this HF is going to break apart and form these two species. Some of the H plus ions and F minus ions in solution are going to find each other and form HF again. Memorize your list of strong acids and bases, and you won't have to worry after that because if it doesn't fit in your list, you know that it's weak. We do have to go through a little bit of acid-base definition here. So there are 3 definitions that we use for acids and bases. We have the Arrhenius definition, the Lewis definition, and the Bronsted-Lowry definition. First semester, we focus more on the Arrhenius definition. Second semester, we focus a lot more on the Bronsted-Lowry, a little bit on Lewis, and then in organic, you're going to use the Lewis definition a lot more. So, the Arrhenius definition. Again, this really focused on in Gen Chem 1. An acid is defined as a substance that produces H plus or H3O plus ions in an aqueous solution. Why could it be H plus or H3O plus? Well, the truth is, when I take HCl and dissolve this in water, I usually write it like this, showing these two things breaking apart. But the truth is, this is surrounded by water. So what's really happening here is this HCl sees a water molecule, and it donates that proton to form the hydronium ion and the chloride ion. But H plus is equivalent to H3O plus. So we can say H plus or H3O plus. An acid is anything that produces that in solution. A base is anything that produces OH minus ions in solution. So sodium hydroxide is our most common base source. If I take sodium hydroxide and put that in water, I get sodium ions. These behave as spectators. We're going to talk about spectators in another video in this chapter. And hydroxide ions. Hence, it has formed hydroxide ions in an aqueous solution. I really like this pictogram here. This is from a girl on Twitter called The Bumbling Biochemist. I highly recommend you check her work out. She's got some great cartoons that just explain things a lot easier. She's, I believe, a master's student. But she's got some great ways to just better explain what's really going on here. And so when she talks about acids and bases, it's, say you have a cookie jar that's partially full and you invite over some friends. Your cookie jar, we're going to call it your proton jar. Remember, proton is H plus. We've lost one electron. All we have left is our proton. Strong acids come with cookies that they really want to give away. They don't care how full the jar is. They want to give their cookies away. They're the ones that come to the party every time with a bunch of things to share for everyone, and they want everyone to take it, and they don't want to take anything home. Weak acids, though, some come with cookies. Your weak acid people are going to come with cookies, but they'd rather keep them to themselves unless the jar is running really low. If you actually really need their cookies, they're going to share them, of course. But they want to hold on to them until they realize that, yeah, these are actually necessary to share. Otherwise, I'll just keep them to myself. On the other side of that, you've got your bases. Some bases are really greedy. Some aren't quite as greedy. Your strong bases are really, really greedy. They will take the cookies even if the jar is low. They're the person that's going to take that last piece of pizza without asking anyone else in the room if they want one. Whereas your weak bases, they don't want to take them away from other people who want them. So they're not going to take them until everyone's taken one and there's a lot left over. So your strong acids and strong bases are the two extremes. Strong acids giving away all their cookies that they brought to the party. Strong bases eating everything they can in sight. Weak acids and weak bases are the middle ground here. Weak acids donating if they need to, but only if they need to. And weak bases taking, but only once everyone has what they want. your Bronsted-Lowry definition and your Lewis acid definition. Again, Bronsted-Lowry we're going to use a lot more in Gen Chem 2, but you do have to understand the definition. Bronsted-Lowry is defined as, an acid is defined as a substance that donates a proton. So in Arrhenius definitions, we said it produces H+. In Bronsted-Lowry, we're saying it's donating that proton. So HCl still fits the bill here. HCl reacts with water, giving me H3O plus Cl minus. The HCl here donated a proton to the water, leaving just the Cl minus behind. The water accepted the proton. So a substance that accepts the proton is a base. Water can actually act as a proton, as an acid or a base under Bronsted-Lowry conditions. Water can both accept a proton and donate a proton because water can go between H3O plus, H2O, and OH minus. We'll talk about a lot more about that second semester. But that HCl donated that proton. Therefore, HCl is acting as an acid. Water accepted the proton. Therefore, water is acting as a base. The other one we have is the Lewis acid-base definitions, and this comes a lot more prevalent in organic. This one we talk about electron pair donor and electron pair acceptor. We haven't done Lewis structures yet. We will do them in chapter 10, but if we were to draw these out in Lewis structure form, our HCl is sharing 2 electrons between the hydrogen and the chlorine. We react this with water. We form the chloride ion and the hydronium ion. I realize I'm going to turn this hydrogen down here in pink so that we can see him over Cookie Monster. And this is aqueous here too. So here, what we see, so an acid is an electron pair acceptor. This is our acid. It loses the proton. The chlorine accepts that pair of electrons that was left behind when the hydrogen left. The base is an electron pair donor. The oxygen has 2 lone pairs on it, and it donates this pair of electrons to form a bond with the hydrogen. Again, there are 3 definitions. Arrhenius is primarily used in Gen Chem 1, Bronsted-Lowry primarily used in Gen Chem 2, and Lewis acid-base primarily used in organic, but that does not mean you're not responsible for them, because I say primarily, that doesn't mean we don't use the other ones. And then just another picture showing acids from the Bumbling Biochemist. So for acids, again, they bring cookies out of the jar. They may or may not be charged. They can bring 1 cookie, meaning it's monoprotic, or more than 1 cookie, multiprotic. We can have diprotic acids, triprotic acids, meaning they can have more than 1 proton they can lose. Hydrochloric acid is a monoprotic acid. Sulfuric acid is a diprotic acid. Phosphoric acid is a triprotic acid. This loses its 1 proton. This loses 2 protons. This loses 3 protons. Strong acids come with cookies they really want to give away. They don't care how full the jar is. Weak acids come with cookies they want to keep unless the jar is running low. Again, bases are going to take the cookies from the jar. These cookies may or may not be charged, meaning ions. When I say charged, I mean ion. Again, strong bases are going to take it no matter what. As long as there's something there, the strong base is going to take it. They're going to take until there's nothing more. And a weak base will take it, but only once there's a lot left for everyone else. So here are your strong acids and strong bases that you must memorize. There's just no exceptions to this. You just got to memorize these things. Brute force, I don't know, whatever works for you. I will tell you these go together. These are halogens. Note HF is a weak acid. So if you look at your halogens, you've got fluorine, then chlorine, then bromine, then iodine. These are your strongs. This is weak. We've got nitric, which is our other monoprotic strong acid on this list at least. We've also got perchloric and chloric that are monoprotic strong acids, but remember, this is like learning chlorate. If I put chlorate is ClO3 minus. If I give it a proton, that becomes chloric acid. Remember the naming from naming acids rules that we covered in chapter 3. And perchlorate becomes perchloric acid. And then sulfuric acid is most produced chemical worldwide, last I knew. Maybe not now, but that's last time I checked it was. Used everywhere. And it is a diprotic acid, meaning it has 2 protons it can lose. There's not much rhyme or reason to memorizing those other than we do have the halogens there, and then perchloric acid and chloric acid go together. But the strong bases are a little bit easier, at least for me, to memorize. When you look at your strong bases, you see here we've got lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Note, these all fall in group 1. They are group 1 alkali metal. We call them alkali metal hydroxides. So find lithium and count down 5 spots. There's 8 total strong bases, 7 strong acids. So 6, 7, and 8, calcium, strontium, and barium hydroxide. These are group 2. They're alkaline earth hydroxides. The trick to these, group 1 is easy. You count down 5 spots. Group 2, you got to remember 3, but you cannot start until you get to calcium. Beryllium hydroxide and magnesium hydroxide do not fit the bill of strong bases because they're just not that soluble in water. And in order to behave as a defined strong base, you have to be completely soluble in water. So we start at calcium, and if you can remember to start at calcium and count 3 down, that can help you memorize your strong bases. So what is a salt? I've talked about it a little bit, but I don't know if I've actually defined it. A salt is any ionic compound whose cation is not H+, and whose anion is not OH-. Because if the cation was H+, it would be an acid. If its anion was OH-, it would be a base. So an ionic compound does not have H+ or OH-, its cation or anion is a salt. We can have metal salts, well, they're going to be metal salts, but we can have like transition metal salts, meaning like a zinc salt, a copper salt, a nickel salt, iron salt. We can also have them from our main group metals, so like our group 1 and group 2, sodium chloride, magnesium bromide, those are salts. It is also the product of an acid-base reaction. So if I take hydrochloric acid, HCl, I react this with sodium hydroxide, NaOH, I'm going to produce NaCl and water. NaCl is table salt. There's not getting anywhere away from that salt. So the thing that people often forget about, though, is this concept of a metal salt. Technically, we know that sodium is a metal, but people don't think about it as a metal. So when I say metal salt, I mean really think about like your transition metals. It's a metal cation with a nonmetal anion, and they form a soluble compound. So we need to know what our solubility rules are to be able to go on with this section. Here are our general solubility rules, and you can find these in your book as well. Group 1 salts. What do I mean by group 1? I mean any element in group 1. So your alkali metals. Anything paired up with potassium, sodium, cesium, rubidium, I'm forgetting lithium, anything paired up with a group 1 metal, so therefore is called a group 1 salt, will be soluble. I don't care what it is soluble. Sodium bromide, sodium iodide, sodium sulfide, they are soluble. Ammonium. Hopefully you guys remember your polyatomics by now. If you don't, learn them quick. Anything paired up with ammonium is always soluble. Ammonium with another polyatomic, ammonium phosphate, ammonium nitrate, ammonium with a non-metal, ammonium chloride, ammonium bromide, ammonium iodide, ammonium sulfide. They are always soluble. And what do I mean by soluble? I mean they dissolve in water. Nitrate, perchlorate, and acetate. Your book more often writes acetate like this. You're going to see me write it as CH3COO-. I try to write it both ways. When I write it on the board, oops, wrong button. When I write it on the board, I'm going to write it like this. I try to write it like this because I know that's what your book uses, but again, I'm not good at it and I don't think about it. Always soluble. I don't care what they're paired up with, they're soluble. Chloride, bromide, and iodide. They are usually soluble, but not always. If you have chloride paired up with copper 1 specifically, silver, mercury 1, remember Hg2, 2+ is mercury 1, or lead 2+. It is not soluble. These will be insoluble. So if I have CuCl, it forms a solid, but if I have CuCl2, it's going to be soluble. So you have to pay attention to the charge states here. Sulfate. Things paired up with sulfate are usually soluble. Exceptions to that are calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, mercury 1 sulfate, and lead 2 sulfate. Those will be insoluble. Hydroxides are usually insoluble. The exceptions to that are your strong bases. Strong bases, by definition, are highly soluble. They're actually dissolve or dissociate 100% in solution. So by definition, they have to be soluble. Carbonate and phosphate. Are usually insoluble. The exceptions to that are group 1 cations and ammonium. But since these are always soluble, that shouldn't be too much of a surprise. And sulfide, usually insoluble. Exceptions to that, groups 1 and 2 cations and ammonium will be soluble. Work on memorizing those, but let's go ahead and work some examples. What I want you to do in this section is identify if the compounds will be soluble or insoluble. This means in water. So silver chloride. Chlorides are usually soluble unless they are paired up with copper 1, mercury 1, lead 2+, or silver. This will be insoluble. Sodium phosphate. And I'm going to use S for soluble and I for insoluble. Sodium phosphate. Phosphates are usually insoluble, but if they are paired up with a group 1 cation, they are soluble. Copper sulfate. Note here, copper can have 2 oxidation states. This is copper 2 sulfate. Copper 2 sulfate is soluble. Sulfates are usually soluble. This is not an exception, so this will be soluble. Copper hydroxide, copper 2 hydroxide specifically. We have 2 hydroxides there, so copper 2 hydroxide. Hydroxides are usually insoluble. The only exception is strong bases, so this will be insoluble. Aluminum hydroxide, same reasoning as before. Hydroxides are usually insoluble. They're only soluble if it's a strong base. This is not a strong base, so this will be insoluble. Strontium hydroxide. Strontium hydroxide is a strong base, so this will be soluble. Zinc nitrate. Zinc isn't anywhere on my solubility rules. However, nitrate is. And it says nitrate is always soluble, so I know this will be soluble. And barium perchlorate. Barium is listed on my tables with some exceptions, but not listed with perchlorate at all. Perchlorate tells me it's always soluble, so this will be soluble. If you cannot identify its solubility based on the table, one half of it at least will be on the table. If you can't identify it from that, you're not responsible for it. But there's a lot of combinations we can do off that table just by giving you one half or the other, and you are responsible for identifying that. So, soluble or insoluble, and then for the first table, and then we're going to go through strong or weak for the second. Let's go ahead and look at what we've got. How about sodium nitrate? Do you guys think that's soluble or insoluble? Well, you've got sodium, which is group 1, always soluble, and you've got nitrate, which is always soluble. So that is most definitely soluble. Sodium hydroxide, strong base, soluble. Oh, I missed barium sulfate. Barium sulfate, sulfates, usually soluble, but not always. One of the exceptions to sulfate is barium, so this will be insoluble. Let's see, potassium carbonate. Carbonates are usually insoluble, but if they are with group 1 cations or ammonium, they will be soluble. Potassium is a group 1 metal, so this will be soluble. Silver chloride. Silver chloride is AgCl. We just did that on the previous table. This is looking at names instead of formulas. So making sure you're still realizing sodium chloride. Chlorides are usually soluble, but not with silver. Ammonium chromate. Chromate is not on my list, but ammonium is. And it tells me ammonium is always soluble. Lithium sulfide. Sulfides are usually insoluble, but the exception to these rules are groups 1 and 2 cations and ammonium. Lithium is a group 1 metal. Barium sulfide. Sulfide again, usually insoluble, but groups 1 and 2 cations along with ammonium are soluble, are exceptions to the rules, so this will be soluble. Copper 2 nitrate, that means copper 2 plus. Copper 1 plus 1 is an exception, meaning it's insoluble sometimes, but that's with halides or halogens. Nitrate is always soluble, so this will be soluble. And calcium chloride. Chlorides, usually soluble. They have some exceptions, but calcium is not an exception, so this will be soluble. Okay, how about our strong and weak acids? Or strong and weak acids or bases. Sodium hydroxide. That is a strong base. Calcium hydroxide, strong base. Iron hydroxide, that is a weak base. It's not one of the ones I have memorized. Acetic acid is a weak acid. Technically, I have it memorized because we use it all the time. It's the active ingredient in vinegar, but it's not one of my 7 strong acids I've memorized. Hydrochloric acid, strong acid. I have that one memorized. Ammonia, weak base. It's not one of my 8 that I have memorized. Perchloric acid, strong acid. Hydrofluoric acid. Again, this one throws students off because HCl, HBr, and HI are strong, but HF is above that, and it is in fact weak. Carbonic acid. Carbonic acid is when we bubble CO2 through water. It's what actually makes the bubbles in your pop. is a weak acid. Nitric acid, you'll hear some people call that nitric acid. I call it nitric acid. It is a strong acid. It hurts really bad when you drop it on yourself. I know from experience. Used it a lot in grad school and didn't always follow PPE rules like I should have. And I definitely paid the price for that. Sulfuric acid, strong acid. And hydrosulfuric acid, weak acid. Don't mix those up. The hydrosulfuric and sulfuric are not the same thing. Hydrosulfuric would be like H2S. And one more example. Which of the following dissociates significantly in water? Can we identify that? Calcium phosphate. What do I mean by dissociate significantly in water? I mean that they are either soluble salts, strong acids, or strong bases. So, breaks apart into ions. They're soluble compounds. That CPDS means compounds. So your strong electrolytes, strong acids, and strong bases. Calcium phosphate. Calcium phosphate. Do we remember the rules for our solubility rules? What do we know about phosphates? Phosphates are usually insoluble. Exceptions are group 1 cations and ammonium. This is not a group 1 cation or ammonium. So this is going to be a giant no. Let me change this to white so you guys can see it a little bit better. What about sodium carbonate? Carbonates are often insoluble, but when with group 1 metals, they are soluble. So yes, this will dissociate significantly in water. Iron 3 hydroxide. Hydroxides are bases, but this is not one of your strong bases. So this will not dissociate significantly in water. Acetic acid, not a strong acid. Ammonia, it is a base, but it is a weak base. Silver iodide. Iodide is usually soluble in water, but one of the exceptions is silver compounds. Silver iodide is not going to dissociate significantly in water. Barium chloride. Chlorides like to dissociate in water. The exceptions are copper +1, silver, mercury 1, and lead 2+. So yes, this will dissociate significantly in water. Sulfates. Sulfates, or strontium sulfate. Sulfates like to dissociate in water. They do like to dissociate. They're usually soluble, but exceptions are calcium, strontium, barium, silver, mercury 1, and lead 2+. I know I just read a bunch of those off really fast. Go back to your rules and look at them. The second exception to this being soluble is strontium. Sr is strontium. So no, this is not going to dissociate significantly in water. Lithium chloride. Chloride ions are usually just soluble in water, and group 1, lithium's a group 1 metal, always soluble. Lead 4 nitrate. Lead 2+ is an exception in many of our cases. Lead 4 is not listed at all, and nitrate is always soluble. Ammonium sulfide. Ammonium, always soluble. Hydrochloric acid is a strong acid, so yes, it will dissociate. Perchloric acid, strong acid. Cobalt 3 nitrate, nitrates are always soluble. Tin 2 chromate. Now, this one is not actually on our table at all. So you guys, I won't ask you guys this one directly. I should have taken this one on my notes, and I apologize, but this one is actually not very soluble. Sodium hydroxide, or sodium hydrogen carbonate. So sodium hydrogen carbonate. Got carbonate, which is not usually soluble, but it is with a group 1 sodium, but it says hydrogen in there too. This is baking soda. Baking soda definitely dissociates in water. Magnesium hydroxide. No. Magnesium and beryllium hydroxides are two that are the weak acids in your group 2 metals. They're weak because they don't dissociate significantly in water. Silver acetate. Acetates are always soluble. Silver acetate is one of the few silver compounds that will dissolve. Silver acetate and silver nitrate are the two common ways we can get silver ions in solution. Cesium iodide. Iodide, usually soluble, but it does have some exceptions. This is not an exception, and it will be soluble. And hydrobromic acid, HBr, strong acid, and yes, it is soluble. Practice through these, work through your solubility rules, and make sure you're comfortable with these. They should be very quick in your mind, and it will make the rest of this chapter a lot easier.